Carbonyl chemistry will be discussed in chapter 20. In addition, we will talk about reduction, a little bit about oxidation, and of course, at last, the organometallic reagents, such as Grignard reagents and organolithium, organocopper reagents. But let's begin with carbonyl compounds. So the reactivity of carbonyl compounds. So let's begin by saying that the carbonyl group is arguably the most important functional groups in organic chemistry because of its importance in biological processes and because there are plenty of reactions that involve the carbonyl group. We will, when we meet in class, talk about a few examples of how important it is in biochemistry, but I'll give you an example. Amino acids, they have a carbonyl group. Aspirin has a carbonyl group in it. Enzymes, how they function, how they work. Ketones in the body, they're called ketone bodies, like the ketosis and this keto diet. All of this is carbonyl chemistry. So let's begin by just talking briefly about the basics of carbonyl chemistry. So the carbonyl group looks like this. So you have a carbon atom double bonded to an oxygen atom, where this is delta minus and this is delta plus. Now, it's important to talk about what is happening in terms of the overlap. So you have a sigma and a pi bond, and the pi bond is made up of the p orbitals that are on carbon and oxygen, as we discussed plenty of times how pi bonds are formed. So remember, pi bonds are formed when you have the overlap between p orbitals. So that's a pi bond. And then you have a sigma bond in the middle. Now let's move on to talk about the two major types of carbonyl compounds. So the substituent, this is a very important statement. The substituents attached to the carbonyl group strongly affect the reactivity of carbonyl compounds. What you are going to learn in the next, about the next 4 or 5 chapters, is how changing one group here on the carbonyl compound will create a new reactivity for the compound, will have its own reactivity for the compound. Of course, there are patterns, but there are, of course, specific reactions for these substituents. So let's talk about the two major types of carbonyl compounds. This is very important before we begin. You have to keep in mind that we're talking about two types, type 1 and type 2. So you have to remember what type 1 is, and you have to remember what type 2 is. It is very, very important that you remember these patterns, because the reactions will follow these, will be based on these functional groups. So you have an acyl group, which is this group right here. This is the acyl group. And of course, this compound is an aldehyde. We have an H right there. We also have an acyl group here as well, but this whole thing, so this is acyl, but since we have an R group there, then this whole thing becomes a ketone. So we have an aldehyde and we have a ketone. So notice that there are two groups here. We have an H, that's what makes an aldehyde, and we have an R group, which is an alkyl group. There are a few things. So we have R and H. There are a few things we need to remember about R and H, is that they have no lone pairs on them. There are no lone pairs on them. So they have no lone pairs. And two, and this is very important, is that they cannot be leaving groups. And the reason why they can't be leaving groups is because they are strong, unstable bases. The pKa's of the conjugate acid of the R, which is RH, would be around 50. And the pKa of H2, the conjugate acid of H, or H minus, would be around 36. So these are highly basic, which makes them very strong bases and unstable bases. So that's part one, or type one. Type two is where you have a leaving group, or at least the potential of having a leaving group. And in this case, what we have is the groups, as you see, denoted in Z. So we will call Z, and this should be Z. Not sure why it changed, switch to L. Z right here. So once again, you have your acyl group, and Z, of course, is a leaving group. And of course, Z has lone pairs. So just imagine, we can put the lone pairs on those, on the N, on the O and OR, in OH, right there. So they all have lone pairs. So here's an example. If we were to draw a simple example, something like carboxylic acid. So again, this would be Z. Or you could have an ester, etc. So this is carboxylic acid. In this case, it's acetic acid, which is found in vinegar. So both types, 1 and 2, carbonyl compounds are electrophilic, and it's for a very simple reason. So if we were to draw the resonance structures, all we have to do is, if you draw the resonance structure, you would move the pi bond electrons so you'll have a negative now on the oxygen, and of course the carbon will be positive. So this is the resonance, these are the resonance structures. And of course, even if you didn't draw the resonance structure, just like I showed you on the last slide, that if you just put the delta, the partial positive, partial negative charges, that they would go the following way. carbon is less electronegative than oxygen. So once again, this carbon, which is what we call the carbonyl carbon, is electrophilic. So it's a target of an attack from other compounds or other nucleophiles. Electrophilic. So since a deficiency in electron density, then that makes it prone to an attack. So there are the carbonyl carbon with a partial positive is quite electrophilic. Nucleophilic attack at the carbonyl carbon is often seen the following way. So as I was just describing, if we had the carbon here, and again, this is delta positive, and this is delta negative. And if we have a nucleophile, then that nucleophile is more than happy to attack this carbon, simply because this would be, you can say, electron poor. And of course, this is electron, oops, not this. I mean, it is, but we'll call the nucleophile electron rich. So we have electron poor and electron rich. So if that reaction takes place, in terms of what we call an addition reaction, then the nucleophile would be attached on one end, the oxygen on the other end. Just like that. So that would be an addition. That would be an addition reaction, meaning you added the nucleophile and now you have an extra atom or group to the compound. Here you had a carbon, whatever was attached on here, whether they are alkyl groups, and the oxygen, and now you have all of the previous atoms in addition to the nucleophile. So type 2 carbonyl compounds contain a group that is either a good leaving group or maybe converted to a good leaving group by protonation. So following addition, so if we, once again, if we redraw this, and we have our nucleophile. And now let's add our group, which is Z. And let's just show some lone pairs on it, at least one lone pair, so we can always denote that it has a lone pair. Once the nucleophile attacks, just like it did in the previous step, something else happens, or that's different. So let's show you that. This one goes there, by the way. Same thing. So you have now the carbon in the middle. You have the nucleophile. You have the oxygen. And you have Z. So what's going to happen now that's different is that the carbonyl will form again by bringing these electrons down to form a pi bond between oxygen and the carbon, just like it was there before. and that results in expelling Z out. So you had an addition, but that addition is now followed by an elimination. So you can probably predict how it should look like. You can pause and draw the structure of the final structure of the compound, and it would be the C attached to the nucleophile, and of course the carbonyl oxygen. Very good. So this gives a product where Z has been replaced by the nucleophile, and so the overall reaction is the following. You have Z, nucleophile attacks, and the nucleophile now replaces Z. And you have, of course, Z out. So to give you an example of this reaction, we'll show you. So if we have an acid chloride, and if we react this with lithium aluminum hydride, which is this, but just focus on the lithium, the aluminum hydride. So what would happen is if the electrons in this bond, and you've seen this in the aromatics chapter, if they add as a nucleophile, if you add this hydrogen with its electrons as a nucleophile, so there's 2 electrons right there, then you would have here's H. So this is the addition. Now, once again, we can put the electrons on the chlorine. And once again, when the carbonyl oxygen reforms that pi bond, then what it does is that it eliminates the chloride and you would have now an aldehyde as your product. So this is, of course, elimination. So just to finish this off, let's now look at the same example, the same nucleophile, but now with type 1 compounds, and that's either a ketone or an aldehyde. So let's actually begin with an aldehyde. So suppose you have And once again, we have the aluminum hydride. I know you're typically used to seeing a nucleophile on its own and attacks with its lone pairs, but not with some of the reactions that we will examine, at least in this chapter. So what's happening here is, there's a minus here, is that, and let's put an R group here, so that makes it an acyl group. We'll just make it a methyl so that you can see it as a real example. So notice what's going to happen now is that you're adding that H. So this is the addition. And of course, you would have the carbon in the middle, oxygen. We'll put them on here so you can see them. Here's the H, and here's the other H, and here's the R. So I'm going to circle the H that I added. So this H, is it right? That one right there. So notice now here is you have no leaving group. You can't just simply kick out. It's almost impossible to kick out an H or an R group. Very, very basic. So they are very unstable bases. So in this case, you have no leaving group. So then the next step would be to simply protonate. And be satisfied in a second step. So we'll say protonation of charged oxygen atom. Whether you use water or an acid. And we will end up with an alcohol. So you have an alcohol now. It looks a little bit ugly. Let me redraw this. I know this is an R group. Let me just change this to a methyl. So this is ethanol. So you ended up with an alcohol in this case. An alcohol. An alcohol. Notice that there was no step where you had to expel the leaving group, because there are no leaving groups in this compound. So it does not contain a leaving group, in this case the aldehyde. So you only had an addition reaction, whereas in the one before you had an addition and an elimination. Which ends up being, if you think about it, a substitution. That's why we call it a substitution, nucleophilic acyl substitution, because you have an acyl group. So that's for now. When we come back, we will learn about the properties of those, and those both types 1 and 2, and of course end up going to reactions for each.